Great. Thanks a lot for the invitation. It's a pleasure to be here, and I'm learning a lot from the conference. And I should also say I've written notes for this talk, and they maybe will be available online soon. And because of that, I'm going to allow myself the liberty of being a little loose on some details and technical issues. So I want to begin by giving a little survey of the evolution of the notion of automorphic forms. Starting with maybe the version that we've been discussing, which I'll call the classical setting. And in this setting, you consider an automorphic form to be a function on a locally symmetric space, such as maybe take a connected reductive group and I consider some couple coset space. Like so. But there are other notions. So I think it's been understood for a long time that that the theory of global number fields is very similar to, or highly analogous to the theory of global function fields. And in this setting, start with a curve, maybe smooth and projective curve over a finite field, and I'd consider F its field of rational functions. And I can form something that looks very similar. So I can form a space that looks like G of F on G of A. And then here I would put the product over closed points of this curve of G of OV, where this OV is the completed local ring of my curve at the point V. So it's the ring of integers of a local function field. So that a theory of automorphic forms and analysis of automorphic forms on these spaces is pretty analogous, but maybe I'd like to call attention to one fairly big difference, which is that while this space has an interesting geometry, for example, for SL2, maybe it looks something like that. This space, you take some space and you mod out by an open subgroup. And because of that, this space looks discrete. So maybe it doesn't have sort of an interesting geometry. It still has interesting analysis, but not geometry. One way of putting geometry into the picture is by using an observation of Feng. So Feng observed that I can view this set as the set, or maybe I should really say group point, of rational points on an interesting geometric object, which is bun G. And so this bun G is the moduli stack of G bundles over my curve. So if you don't like this so much, feel free to assume that G is GLN in this talk. At some points, you'll have to assume this. You can think of this G bundle as just meaning a vector bundle in that case. So if G is GLN, the G bundle is a vector bundle of rank n. Okay, and then instead of searching for functions on the set of rational points, one could search for automorphic sheaves on bun G. And so this leads into something called a further evolution of this notion, which is called the geometric limits program. And maybe this was pioneered by Drinfeld and Lemma. But since then has seen a lot of contribution by many people. So what I want to do today is introduce and study sort of another direction of taking this thing here and putting some geometry into the situation. So that would be moduli of shtukas. And I want to begin by sort of, let me introduce this space, which I'll call shtuka G superscript 0. This will be a moduli space, and I'll kind of write it informally as as if it were a set, but this means the moduli space of things I'm going to write inside here. So there'll be, E will be a G bundle on X. And I'm going to consider the datum of an isomorphism between the Frobenius pullback of E and E. And let me denote this double coset space by brackets G. The point then is that, as I said, this is a discrete set, or maybe a groupoid, that this thing is the same thing, but considered as an object of algebraic geometry. So this is G as discrete sets, and if I'm being really careful, I need to replace this word sets by groupoid. And what I'm saying is something kind of simple. It's just that there's a thing here, a set. I could consider it as like a zero-dimensional algebraic variety. Okay, any questions about this? So the point is that this is somehow a reformulation of Bayes' theorem here, that I'm giving myself a G bundle and what should be viewed as a kind of descent datum saying that G bundle, whoops, I should say this is an isomorphism. A descent datum saying that G bundle really comes from just a rational point. That's why this is true. It's sort of the same content as Bayes' observation. And I can sort of now reformulate the notion of automorphic form. So then the cohomology of the zero-dimensional object should just be functions on that object or functions on this. So functions on this double coset space, or in other words, automorphic forms. So that seems like a little silly thing to write. But now the point is that we're going to sort of generalize this space in various ways, and we're still going to be interested in its cohomology and view that as a generalization of the notion of automorphic form. So I want to discuss maybe two types of generalizations. And the first one is, here I've required a map to be an isomorphism, and I can instead sort of relax that and allow this map to acquire zeros and poles. So allow phi, which is an isomorphism here, to acquire zeros, poles at points of the curve. So in other words, I'm instead going to ask for a map which is just an isomorphism on a punctured version of the curve. But I'm not going to require that it extends to an isomorphism on the whole curve. So it's a fact that the order of the zero and pole, generalizing this sort of usual notion of the order of a pole of rational function, so the order of pole between a map of G bundles at a point of my curve is kind of measured by an element of, so this is supposed to be a mu, an element of the double coset space G of OV, G of FV, G of OV. And let me just say verbally why this is true. So the idea is that we've got this curve, and we're looking at a point on the curve, little v. So this big curve is x. And near this point v, the bundles, by definition, they're locally trivial, so they will be trivializable in a small neighborhood of v. And you should think of the completed local ring as being the ring of functions on a small neighborhood. And so after I pick a trivialization, I just have to give a map on the punctured neighborhood, which is an element of G of FV. And that was ambiguous up to the choice of trivialization. So I mod out by sort of those choices which are corresponding to G of OV. And I recognize this double coset set in a couple other ways. So it's the same as the this is by the Cartan decomposition. This is the same as the dominant co-characters of G, the set of dominant co-characters of G, which is the same as the set of irreducible representations of G hat. I'm assuming G is split. So anyway, the upshot is that, oh, maybe I'll give an example first. So if G is GL1, we're just talking about line bundles. And a map of line bundles is just the same thing as like a rational function. F. And so what I'm saying is the order of a pole should be measured by characters of GL1, which is Z. And indeed, this sort of matches up with the usual notion of pole order of F. So that's why I think of this as the pole order. Okay, any questions about this? Okay, so the upshot is that given a dominant co-character, mu, I get sort of a generalization of this space. I get a space which I'll call shtuka G superscript mu, which parameterizes a point on the curve and a G bundle on the curve and a map phi which is allowed to have a pole at this point V. So the way I'll write that is that there's kind of a map which is defined away from V. It's allowed to have a pole at V, and that order of that pole is at most mu. Okay, and this space has a map to the curve just by remembering only the point where the pole occurs. So this datum would map to a point on the curve. And one wants to think of this as being kind of analogous to, in the classical setting, I had this double coset space G. Sometimes this is the complex points of an algebraic variety, which would be a Shimura variety attached to some minuscule co-weight, and it's definable over a number of fields, so it lives over spec Z. And this arithmetic curve spec Z is kind of the analog of this geometric curve X. So, and unlike, well, when I take mu to be 0, I get the original double coset space, but in general, this is not a discrete object, so it's an interesting geometric object. Okay, any questions about this? So now I want to consider another direction of generalization. And in this case, I want to sort of allow more points, more pole points. A prime number plays the role of V. Okay, so the definition of the objects are not sort of quite the same, but I'm just saying the structure of a thing over a curve, and somehow this is bound up with automorphic forms and Galois representations. And in that sense, they're similar, but the actual definitions are maybe not so similar. Although, so in some cases, so like this sometimes moduli of abelian varieties, and there's sort of crystalline cohomology, and that has a Frobenius linear map, just not an isomorphism. So there are some common structures. Okay, and so now I want to allow more pole points, meaning I allow this map to acquire poles at multiple points. So let's say I is a finite set, and mu I is a collection of co-characters of G. I could define sort of an even more general object, shtuka G comma I, superscript mu I, and this would parameterize a whole collection of points, Vi, in the curve, and sort of a map between the Frobenius twist of a vector bundle, or of a G bundle and itself, which has poles over all of these VIs potentially, and pole order at VIs bounded by mu I. And this object lives over a larger power of my curve, the ith power of the curve, just by remembering the pole points again. So you could view this as a collection of points in here. And I want to emphasize the fact that now this really doesn't have an analog in the classical setting. I mean, even this x to the I, if x is analogous to spec z, this should be analogous to spec z to the I, but like you can't make, that's just spec z again. You can't really make it in an interesting way. Maybe, so I'll say no classical analog. Okay, so maybe let me summarize what we've seen so far. So there were sort of a couple pictures. There's a sort of classical number field picture, and then there's a kind of function field picture. And here, in the classical setting, you had this double coset space. Functions on it are automorphic forms, and sometimes, let's see, sometimes this is even an object of algebraic geometry. It's a complex points of a Shmurov already. In the function field setting, you had the kind of double coset space, which was not so interesting. It was completely discrete, and it was an object which I called shtukas 0. But you also had the ability to create a lot more of these spaces indexed by an arbitrary dominant co-character of my group. So there's a kind of infinite collection of such things. And we can even go in another direction. We can sort of create objects indexed by a finite set and a finite collection of co-characters. So while here we had sort of one thing, here we kind of have this infinite family of objects. And I want to advocate the point of view that, so as I observed, the cohomology of this initial most trivial shtukas 0 thing, and I'm going to want to take compactly supported cohomology from now on. This kind of, well, this is a space of automorphic forms for G. And I want to advocate the point of view that we should consider the cohomology of these more general objects as well. And that we should think of these as being spaces of the higher automorphic forms. So, I mean, these definitions, they look sort of, they're easy to write down, but I think for a long time, in the function field arithmetic, people were focused on doing things analogous to what number theorists do here, and there wasn't really like an idea of how to actually use this extra structure. But recently, we have seen some interesting ways of using this whole array of objects, a lot of which are inspired by geometric languages. And so what I'm going to talk about today is sort of an exploration of one other way to use this whole story. And I want to maybe mention that, so maybe it was Yun and Zhang who coined this name. And one of the reasons we use this word higher automorphic form is because they showed that in some settings where classically you'd expect a period integral of an automorphic form to be related to a special value of an L function, they showed that kind of analogous period integral of a higher automorphic form is related to the special value of a higher derivative of an L function. So we see that there are some surprises popping up from using these things, which one doesn't have kind of any way to formulate it classically. Okay, so are there any questions about this? All right, not too bad. Okay, so what I want to talk about today is something called the base change fundamental lemma. So let me try to describe what that is. Okay, so the idea of this and sort of all fundamental lemmas is that they provide an exchange rate between two different currencies. And those currencies would be kind of orbital integrals on different groups. So the idea is that if we want to compare, if we want to prove cases of functoriality, if we want to compare representations of two different groups, we look at the trace formula, we take the geometric expansions, and those are both in terms of orbital integrals, but they're orbital integrals on different groups. And if you really wanted to compare that, you'd have to have a way to convert between these two types of orbital integrals. And so in this particular case of base change, what we want to convert between are orbital integrals and twisted orbital integrals. And for the purposes of this talk, kind of what I just said is sort of the only thing you need to take away from this section. If you're not super familiar with the yoga of fundamental lemmas, just remember this principle. But I feel like I probably should try to formulate things a little more precisely. So let me try to do that quickly. So I'm going to want to consider a local field FV. At the moment, it could be either p-adic or function field. I want to tell you quickly what an orbital integral is. So if I give myself an element of G of FV, and I'll let G gamma be the centralizer of gamma inside G, then the orbital integral of some test function f is, so morally it's an orbit of f over the integral of f over the orbit of gamma under conjugation. So I could write that as G mod G gamma of f of G inverse gamma G. Okay, so that's what an orbital integral is. What about the twisted thing? So here I would give myself a field extension of degree r, unramified. And so I can pick, so it's cyclic, and I can pick a generator in the Galois group. And I'll give myself delta and G of E. So that's sort of upstairs. And I'm going to let G sub delta sigma be the twisted centralizer, meaning the set of G's such that G inverse delta sigma of G is delta again. And now the twisted orbital integral is just the integral of a function over a twisted orbit. So TO delta sigma of F is the integral G of E mod G delta sigma. This is the orbit of delta, F G inverse delta sigma of G. Okay, and the base change fundamental lemma is going to tell me how to compare two such objects. So first I'm going to state something I'll call the spherical version. And it says that the twisted orbital integral is equal to the orbital integral over the norm of delta of the base change function. And there's sort of lots of details I'm suppressing, like choice of Haar measures and so forth. But this is the statement. And here I'm assuming G as GLN in order to simplify the statement. So in general, it'll be kind of much more complicated. So I have to explain maybe what the norm and the base change are. So where norm of delta, well, I start with something in G of E. I need to get something in G of F. So it'll be delta times sigma of delta, etc. And this is well defined as a stable conjugacy class, which, because we're talking about GLN, is the same thing as a conjugacy class. And the base change function will go from the spherical Hecke algebra of G of E to the spherical Hecke algebra of G of F. And this is sort of dual to restriction for Galois representation. So this is the spherical Hecke algebra is the functions on kind of the set of unramified Galois representations of the dual group that has a restriction map, and so there you get a base change map that way. Okay, so there's a more general version. We can allow F to be in the center of a paraphoric Hecke algebra. Okay, so this thing is sort of functions, compactly supported functions on the double quotient by a paraphoric subgroup. That's not abelian. I mean, it's not commutative, so except when it's spherical. So when it's spherical, you get back the whole thing, and in general, you can allow F to be in the center of such a thing. There's a Bernstein isomorphism which tells you that these are actually naturally isomorphic as algebras. So you get a base change map for such guys, and otherwise the statement looks exactly the same. Okay, any questions about this? All right, so let me say a little briefly about what results we have. So first, in the case of p-adic fields, local fields, the situation is actually really good. So you know, you have this fundamental lemma in the spherical case in general by a work of Kottwitz and Clozel, independently Labesse. Kottwitz proved it for the unit element, and they independently extended it to the whole Hecke algebra. So for the spherical Hecke algebra. And Tom Haynes for paraphoric Hecke algebras. That's a generalization. And in the case of local function fields, the situation actually is a little bit worse. So here, go explain how to do it for GLN. And again, for the spherical thing, spherical Hecke algebra. And kind of, the way it's written, you don't really get this. So really what you get is like the Hecke algebra of SLN inside the Hecke algebra of GLN. But okay, you almost get it. And so I guess my result was that in the exact same setting, so GLN again, you can get it using for the paraphoric Hecke algebras. And again, sort of, there's an asterisk. It's almost in the same sense. So there's kind of a natural strategy to go from this almost to the whole Hecke algebra, but neither of us have suffered through the pain of carrying that out yet. And I'll maybe remark that the proofs in this case are analytic and use the trace formula, whereas the proofs in this case are geometric, and I'll be talking about them the rest of the talk. Okay, are there any questions about this? All right, so let me mention an application. There's a few applications of this fundamental lemma, but let me mention one which is also going to be relevant in terms of framing the proof. Okay, so the application would be the base change problem from automorphic representations of the of G of AF to G of AE for cyclic extension E over F. So this is an instance of functoriality between G and the restriction of scalars from E to F of G, base change to E. Let's say. And the idea for doing this is that you have the trace formula, which tells you what representations are, what automorphic representations there are, and you want to compare the trace formula for G of AF with the twisted trace formula for G of AE, and kind of you expand out the geometric sides, and on one side you get orbital integrals, and the other side you get twisted orbital integrals, and you better have a way to convert between them if you want to show that they're equal. Okay, so so what I want to talk about next is the idea of the proof. And the idea is due to Go, and I'll present my perspective on it. And maybe the starting point is to consider, so this is a hard problem, but the starting point is to consider maybe a much more degenerate problem. A more degenerate problem is sort of functoriality between, so let's replace E by kind of the trivial algebra extension F to the R, in which case the restriction of scalars of G just becomes G to the R. Now base change between G and G to the R is kind of trivial, so you just take a representation of G and you take its Rth tensor power. But let's play along and imagine like what the trace formula comparison looks like in this case. So it comes down to the following exercise in algebra. If you have a collection of endomorphisms of a vector space, then the trace of the tensor product of these things composed with the cyclic rotation automorphism of V tensor R. So this is the thing which shifts each factor by 1. So this is like a twisted trace. This is equal to the trace of the product of these Fs on just V. And that, a consequence of this is that kind of the twisted trace of a collection of elements of the Hecke algebra composed with automorphism of G to the R, cyclic rotation, on the cohomology of this kind of trivial shtuka for G to the R is equal to the trace of this product, let me call it multiplications of the Fs. On the cohomology of trivial shtuka for G. So as we've discussed, this is I'm also going to continue on to use compactly supported cohomology. So this is a sort of avatar of automorphic functions on G to the R. This is the twisted trace. It's just equal by this lemma to the trace on automorphic forms of G. So maybe this is not super interesting, but it becomes interesting if we start to ask ourselves, what's a sort of higher version of this? In other words, suppose I, still on the board? No. suppose I was looking at the cohomology of these more interesting moduli spaces, which I introduced in the beginning, then what does this analog of this look like? So we should look at a space of shtukas for g to the r, meaning I'll have to specify a sequence of co-weights for g. And I want to compare this to some other space, which is a space of shtukas for g. And it's already a sort of a little subtle to pinpoint what the right answer is. So I'll tell you what it is. The answer will be something which I'm going to call shtuka g r dot mu. And it parameterizes the datum of a point of the curve and a sequence of maps between vector bundles. Okay, and so these, they all are allowed to have poles over this point V of order bounded by this co-weight mu. And this space, again, lives over the curve x, just by remembering the data of this point. So we've got two spaces over x. And now the right version of this trace comparison is to compare. So let's call this map pi and pi prime. Let's compare the cohomology of pi and pi prime. Okay, so if you're not super familiar with this notation, just think of it as kind of the cohomology of the fibers of these two different maps. All right. Any questions about this? Okay, so let me try to formulate something more precise. So, i.e., we have the following claim, and I'm going to put an asterisk here. So the claim is that the trace of the Hecke algebra for g to the r, of course, is just the sort of r-fold tensor product of the individual Hecke algebras for g. So given a vector of Hecke operators for g, take the trace of this composed with the automorphisms of g to the r, given by cyclic rotation, on the cohomology of a fiber. So cohomology g to the r restricted to the fiber over some point on the curve. And I claim that this is equal to the trace of the product of these Hecke operators composed with, additionally, since we live over the curve, these things have a kind of Galois action. So I want to further compose with the Frobenius. Right? Frobenius at this point of the cohomology of this other space. Okay, so this expression is getting kind of monstrous, but are there any questions about this? Yeah, so as I said, you think of this as a sheaf which kind of has a stalk over each point of the curve given by the cohomology of the fiber. And so I'm just saying for any particular point, x0 on the curve, this is true. So that's some statement about these two sheaves. Okay, and there's an asterisk because like something here is sort of not quite right. But maybe I won't say exactly what exactly should be here. It's basically something like this. The notes contain the details. So I claim that this is sort of a higher version of this trivial comparison of trace formulas. And how might one prove this? So one might try to expand both sides in terms of some sort of geometric expansion and then match things up. And things are a little more complicated because now we're on sort of not the sort of double Coset space that we were working with before, but an enhanced version of it. But still, there's a method which in the characteristic 0 situation was pioneered by Langlands and Kottwitz. This method will give an expansion of this trace in terms of orbital integrals. So there'll be a sum over something, a bunch of factors, and then what turns out to be the case is that on this side you see a twisted orbital integral, some function, and on this side you get something very similar, a sum over the same things, product with all the local factors being pretty much the same, except that here you get an orbital integral of a base change function. So we try to do some sort of trace comparison to know if these are equal, and what we find is that one side is expressed in terms of twisted orbital integrals, so this is kind of the contribution from the factor at x naught, and this is the corresponding contribution from the factor at x naught, and it's exactly the problem of the fundamental lemma. We don't know how to compare these things without the fundamental lemma. But maybe one observation we can take away is that if we somehow knew these were equal for other reasons, then we would have some sort of interesting relation between twisted orbital integrals and orbital integrals. And it's not hard to show, so here's a lemma, and this is an honest lemma, not a fundamental lemma, that, that the claim, not only is it applied by the base change fundamental lemma, but it's actually equivalent to it, or at least in this version I stated. And by the way, the mu here is the same as these mu's here. So it's the flexibility of varying this co-weight over all co-weights of G that gets sort of the fundamental lemma for all elements in the Hecke algebra. So the upshot is, if we could prove this in some other way, if could prove the claim independently of the fundamental lemma, we would deduce the fundamental lemma as a consequence. Okay, so is everyone happy right now? Or at least, are there any questions? Okay, so, and this is what we're going to do. We're going to find another way to perform this comparison. And where that's going to come from, wait, all right, I'll keep that on the board. Well, if we look at what the definition of this is, we've got kind of a sequence of maps, and we've forced all of them to have poles over the same point, little v in x. And as we did before, we could generalize this. We could allow these poles to occur over different points of x. So we can allow pole points to move apart. In other words, instead of this space I've written down here, let's consider another space. I'm just going to call it shtuka b, and it's going to parameterize the datum of a tuple of points vi in x, and then something that looks similar, so a tuple of vector bundles, or sorry, of G bundles, and isogenies between them, except I'm going to let this pole occur over V1, and this one over V2, etc. I should do this better. And the final one over VR. And these are potentially different points, and I'm going to let this one be still. All these pole orders are bounded by the same mu. And I'm going to define shtuka A to be a similar generalization of this term here. So a bundle for G to the R is just the same thing as R different bundles for G, but now I'm going to allow them to have poles over different points. So this will parameterize collection of points Vi in X and Vi which is a rational map with a pole at Vi of order at most mu for each I from 1 to R. Okay, any questions about this? So let's examine this setup here. We started with this. Now we've got something much bigger. Notice that if I force all the VIs to be the same, or let me say it this way. This has a map to X to the R, where R will be the set of numbers from 1 to, brackets R will be the set of numbers from 1 to R. This is a map to X to the R, and so does this, just by remembering these points, Vi. And so we've got these bigger spaces, shtuka A and shtuka B, and they live over X to the R. On the other hand, inside this X to the R, there's this diagonal copy of X, where all the VIs are forced to be equal. And over that diagonal copy, you get exactly the original spaces. So let's call these maps pi A and pi B. So what I suggest to do, instead of trying to prove the claim, I want to prove a better, an even stronger version of the claim, which is that which is that sort of, even for these bigger spaces, the cohomology of the fibers is kind of the same. Okay, so here's another claim. How do I want to say this? The trace of a sequence of Heck operators composed with Frobenius on the fiber here. So let's just say HC star shtuka A restricted to X is equal to the trace of the product of these Heck operators composed with Frobenius at the same fiber for shtuka B. For all X in X to the R. And okay, so there's a similar asterisk here as there was there. Okay, so a priori this claim is just strictly stronger than this one. I mean, if I specialize the point of X to the R to be on the diagonal, then I just get the old claim back. So there's no way that there seems to be no way that this could be easier to prove than that one. But what we've gained in formulating this stronger claim is that we now see the problem as kind of natural resolution, and that gives us more flexibility. So the idea is that here's this X to the R, and before we were interested in proving something over the diagonal copy of X. And all the points on the diagonal are kind of degenerate points on X to the R. So what we're going to try to do is say, we're going to prove this second claim on non-degenerate points, or on some sort of open subset where these coordinates are actually distinct. And then deduce by continuity that that equality holds over this diagonal as well. So let's say that we restrict our attention to the open dense subset of points of X to the R where the coordinates are actually distinct. So that's sort of opposite of the original problem. And what I'm saying is that by some sort of continuity principle, if you know that these are equal over this open dense subset, you can deduce that they're equal over the diagonal. Okay, so now this is genuinely different from that. And how are we going to prove this? by kind of the same argument. Compute both sides, a geometric expansion for both sides, and try to equate them. And the interesting thing that one does is when you do this, what you find is that these expansions, they no longer have any twistedness. So you get a sum, lots of factors, and then just an orbital integral on this side. And here, you get a sum over the same stuff, factors which are the same, and then an orbital integral. And now both sides are in the same currency, and you don't need any fundamental limit to compare them. You can just sort of do it directly. Okay, so that was a kind of convoluted argument, so let me try and summarize the structure of it. So the summary is, maybe step 0, we had some motivation. The motivation was to compare the automorphic representation theory of the Bay restriction of G from a field extension and G. So this is a global problem. And using the trace formula and a comparison of such, so by the trace formula, we reduce this to a local problem, which is to compare twisted orbital integrals and orbital integrals. And then we considered, so this was maybe step 1, and this thing, in principle, we should be able to perform this reduction. I'm not saying anyone actually has. In the arithmetic setting, it has been done for GLN by Arthur Coset. Okay, then we wrote down a different global problem. A much more degenerate global problem, which is to compare G to the R and G. But it was a higher comparison. Higher in the sense that I described earlier, in the sense that you take sort of more interesting moduli. You interpret automorphic forms as higher cohomology of higher dimensional moduli stacks of shtukas. And this problem by the Langlands-Kotwitz method, so basically the analog of the trace formula for these objects, these higher objects, it also reduces to this local question, but that reduction can be reversed. These are just equivalent. So we could view this as saying that we've reduced this local question back to a different global question. And then we somehow deformed this global question to yet another global question. So different comparison of G to the R and G. So this deformation used algebraic geometry, and it's one which we could not have carried out in characteristic 0 because the objects, like this sort of bigger object in X to the R, these objects don't exist in characteristic 0. So this was some sort of continuity argument. You deform a statement on the diagonal to a statement off the diagonal. And finally, again applying this trace formula, analog of the trace formula, so the Langlands-Kotwitz method, one reduces this to yet another local question, which is then just a comparison of orbital integrals and orbital integrals. And this just can be done directly. So that was the scheme of the proof. Okay, any questions about this? Yeah. The Galois action basically is the same as saying that things are over the curve, because the Galois group is like the fundamental group of the curve, or maybe some open subset of the curve. Galois action is just another way of saying that things live over the curve. Is that okay? It's the same as if I consider the restriction of scalars from a field extension of G. That's just over the original F. Yeah, right. So that I haven't explained, and it's kind of, in some sense, one just has to do the computation. But maybe intuitively, the idea is like really, like, you should be getting orbital integrals, but somehow when you head to this very degenerate stratum, things come together in a way. So on one side, Heck operators come together, and that forms a base change, and the other side, kind of points come together, and that forms like the restriction of scalars from a field extension. So there's a computation, a long computation to be done, which I haven't done, but this is just the outcome of that computation. Are there any other questions? Okay, so the scheme I've just described, it's a scheme which applies equally well to the spherical or paraphoric Heck algebra. So in the last section, just to sort of convey the idea that I've done something, I want to sort of describe what additional difficulties arise in the paraphoric situation and how one gets around them. And it all comes from this, this continuity argument, which I kind of skated over very briefly. So is this section 5? Paraphoric case. So first I need to describe what goes right in the spherical case. So as I say, the problem comes from the continuity argument. And what we're trying to say is that, what we wanted to say was that, we wanted to kind of say something like, if you have two different sheaves on two different spaces and you have an equality sort of on a dense open subset, so away, let's just say away from diagonal, although it's actually a little more restrictive than that, but it isn't on some sort of dense subset, then we'd like to say that this kind of implies that you have this equality on delta itself. But actually, this is kind of problematic statement. So one needs to have a certain amount of control over these objects to know that a property like this does, in fact, extend continuously. So something which isn't, basically what you need is that these thingies, like let's say this, but also the analogous statement for B, which I won't write, you need this to be a local system on x to the r, which is some way of saying that kind of nothing weird happens on very small subsets of x to the r. Behaves like it's locally constant. And how does one get something like this? So usually if I see something which says I want something to be a local system, a push forward to be a local system, what I want is that, so I want pi a to be proper, and I want it to be smooth. And I kind of want something about this sheaf as well, but I'm going to suppress that. So a proper smooth map pushes forward a local system to a local system. It's the principle. And is this satisfied in our case? So this is not satisfied, not okay in general. And so we use a trick. We can replace G by sort of highly ramified division algebra. So what I mean, I'm just going to write division algebra, but what I mean is that you replace it by the group of units of a sufficiently ramified division algebra, and that would make things proper, kind of. So the analog of the statement is maybe a little more familiar in the classical setting. So this is okay. This is okay in both the spherical and paraphoric situations. What about the smoothness? So this is, it's not literally true, but it's basically okay. It's basically true with spherical level. And what's actually true is that there's some resolution of singularities, which is smooth, and then kind of the sheaf that you put in is a perverse sheaf corresponding to that resolution of singularities, a small resolution. So basically this is okay. And when I say spherical level, what that means kind of in real life is that you can use, it's okay for the spherical Heck algebra. So in other words, what goes on in the paraphoric cases is a matter of a breakdown of this smoothness principle. Okay, so I'm almost done, but let me just say to get H paraphoric, the second point is problematic. And so let me outline briefly what kind of things, how you should think of this problem. So what this means is that these things will not be locally constant. They will kind of like jump on fibers. So what you need to do is correct this by changing the sheaf. So you use something called nearby cycles. And this is something which kind of, you change the sheaf so that the cohomology does become locally constant. Then you kind of win this free. And maybe the picture to have in mind is that you have like a family of curves, but you kind of pinch, let's say like this, you kind of pinch this loop, and in a special fiber, it gets pinched all the way. And what goes wrong is that the cohomology in degree 1 used to be one-dimensional, or two-dimensional, with these two loops, but in the limit, one of those loops is contracted, and you can see it's not constant. I mean, it drops in the limit. And therefore, what you need to do is make the sheaf bigger. If you make the sheaf bigger, then when you take cohomology, it'll be the same as it was before. So, okay, when you kind of use nearby cycles, you restore the property that cohomology is locally constant, but then you kind of break all these other steps where you computed some sort of trace and got some sort of answer. Now that you've changed the sheaf, those answers have changed. And the difficulty is knowing how they changed. And the nature of the difficulty is that they change in a way that mirrors the singularities which appear here. So you use local models to understand the singularities. Because these shtukas, they're objects of arithmetic nature, and so they're quite complicated. Maybe they look like, a simple case would be like this. And what you want to say is a local model for the singularity happening here is just a node. That's something simpler, and you're not really counting how many nodes. You just need to know the nature of the singularity. But still, the nature of the singularities could be arbitrarily complicated in general. And so maybe another important property to have about these local models is that they have additional algebraic structure. So you choose these models with the structure of convolution. An additional algebraic structure. And the point is somehow that the way in which you change these sheaves is a reflection of singularities which are kind of too complicated to describe quantitatively. So instead you try to describe them qualitatively, and one way of doing that is that one way of making that precise is that you can ensure that they're commutative, that they commute with other sheaves under this convolution. So that's a qualitative property, but it turns out to be sort of special enough that it allows you to exactly pinpoint what happens down in this a priori mysterious procedure. So let me not say any more about that. That's sort of the content of extending from spherical to parahorg. Okay, so thanks for your attention. Oh, yeah. Yeah, so what it means, yeah, so I didn't really clarify this, but actually what it means is that you take like a parahorg level structure at the point where you examine the cohomology. And so part of the problem is even to define like what that should mean. But the hack operators are an auxiliary device which lets you isolate from that global comparison a local comparison. Yeah, you're changing the geometric object, and it acquires singularities like this. Right. So right now it's only for GLN, although kind of the strategy has a more general appeal, I think, And wait, are we still on camera? Okay, so I'm going to confess that I know ways of fixing both of these issues for more general G. So this part, right, this is definitely specific to GLN, but I know a way to fix this. And I don't really know where the first obstruction would be, but kind of, in the end, there has to be an obstruction because of the issue of stability and endoscopy. I frankly don't really know what endoscopy is, so I'm here to learn. So I'm hopeful that something can be done more generally, but at the moment,